Okay, the other like the classification of the fluid flow that we're just gonna see here, and we will have this from now on, and also in the like the next chapters, is about like the type of the flow, depending on the like the type of the like the movement. So we have like a three classifications in this case. The first one is called laminar flow. Laminar flow is, for example, this kind of like the variations over the time of the velocity. In if imagine this is like the pipeline, and this is the across the diameter, you can see the like the variation of the velocity. We can see here there's a this kind of like the velocity variations here. For the laminar flow is always all over the time is just going to be like with the minimum change. You will see all the time like here. It's not going to change. So the flow is just move very slowly, and the viscous flows we have. So for example, this is very similar to the flow under through like the aquifer, and the velocity may be as little as a few meters per year. It's very, very slow. So this is not the like the type of the flow that we know. Not neither this kind of like the river, nor in this kind of like the wide river in mountainous area. But this is something that probably we don't see, because like the movement, as you can see here, is like a very little as like a few meters only per year. However, the other type of the flow, which is a really fast compared to the laminar flow and the chaotic, like the flow, is like the called turbulent flow. Turbulent flow is a very common practice of the flow, and in most cases we have the turbulent flow. So for just have like a good example of that, you can see this like a mountainous stream, or like a wide river. You can see like the turbulent flow. However, we'll see later, even this kind of like the river, the flow running is also the turbulent, but the level of the turbulence might be for this one is a much more than this one. Absolutely. And you can see all over the time, this is the variation of the turbulent flow, and this kind of like the things you can see here. It's not like you cannot like the prepare like the a curve, or like the smooth line here. So this line has got a lot of like the fluctuations here. And just bear in mind, all over the time, even they're just going to be changing. If you have like a point 1, point 2, point 3 of the pipes, you can see they're not going to be the same. So this is like the situation, different situation. Another example, let's just look at this smoking here. Like the smoke comes from the cigarette, and this kind of like the figure you can see at the beginning, the flow is very like you can see like the thread of the like the smoke here. But in sometimes after a while you can see the turbulent flow. The turbulent flow is like the this kind of like the flow of the air spread everywhere. So that is called like the turbulent flow. So there's no like the direction, but in here it's mostly dominated by the velocity. But in here it's just dominated by everything, but it's not as strong as in here. And just bear in mind the situations between or conversion from the laminar to the turbulent flow is called transitional flow. Transitional flow is something in between the turbulent or and laminar flow. So with that introduction, let's just look at how we can identify which flow is laminar and which flow is like a turbulent. Osborne Reynolds is the person who found a type of the flow based on the size of the conduit, which is the diameter, density of the liquid, which is the rho, and the dynamic viscosity. So based on these three parameters, and also the mean velocity. Mean velocity, just bear in mind, in the previous slide, we have this variation, but the mean velocity, you know how to do that. It's like the division of the flow divided by the area. So if you have all three terms here, we can easily, by using the Reynolds formula, this is called Reynolds number. By using the Reynolds number, we can, and this equation, we can easily calculate the or evaluate the level of the flow as like the laminar or turbulence. So in Reynolds here is equal to rho v d divided by mu, dynamic viscosity. And for example, depending on the flow running throughout the pipe or in open channel, for example, if it's like a run throughout the pipes, If the Reynolds number is less than 2000, we can call like the flow is laminar. If the flow is between 2000 4000, we can call it like the transitional. And if the Reynolds number is greater than 4000, we say it's definitely turbulent flow. And for open channel, this range is for 500 for laminar and 2000 for turbulence, and between 500 and 2000 is the transitional. So with that sort of like the range, that you will have this range actually all the time in hand. Let's just go with some simple calculation and see, for example, for a pipe diameter of the 0.1 meters, like a 10 centimeters, very small. We can imagine 10 centimeters pipe carries the water, the rate of the 0.025 cubic meters per second, which is equal to 25 liters per second. Taking the density of the water 1,000 kilograms per cubic meter and dynamic viscosity of 1.005 times 10 to the minus 3 kilogram per meter second. So this has to be a second, sorry, this is a meter second. You need to calculate the Reynolds number of flow and determine whether it is laminar or turbulent. So it's very simple. We have like a Reynolds number. We can substitute everything in the Reynolds number, Reynolds rho Vd over mu, and you need to just calculate first of all the velocity. The velocity is not given here, but the area is given to us, and the diameter is given to us. We can easily calculate by continuity equation. So we just use like the area pi d squared over 4 pi. D is like the 0.1 squared over 4. Velocity can be easily calculated here, which is equal to, sorry, the area is calculated here, which is equal to 7.85 times 10 to the minus 3 square meters. And by using the continuity equation, velocity is equal to Q over A. Sorry. Q over A, and so here we're just gonna say Q is a flow discharge, like a 0.025 divided by 7.85 times to the minus 3. So all of them are in denominator, just bear in mind. And the answer velocity is like a 3.18 meters per second. 3.18 meters per second is not too much high. It's a very like the common like the velocity. But let's say, but relatively like a little bit high for the pipe. But let's see what is the like the Reynolds. Reynolds here is like a rho Vd over mu. So rho is like 1,000, V is a 3.18 or 18 times 0.1 diameter divided by mu is given to us 1.005 times 10 to the minus 3, all of them denominator. So the answer is 316,400 is definitely much more greater than 4,000. Just bear in mind, once you're just going to compare this one, you can easily write as a scientific form, 3.16 times 10 to the 5th. So we're just going to, this is like a 3 significant figures here. And but this one has got 4 significant figures, bear in mind. So it's definitely a turbulent flow. You can see for this kind of like the flow, how big or the magnitude of this one compared to the 4,000. So you can imagine for a very small flow as well, for very small like the velocity, in many cases we have this sort of turbulent situation. So that is the turbulent and the different types of the flow regime.